Hi everyone, my name is Waldy. Today I'll be presenting a paper that I co-authored with Professor Hoong Chuin. The both of us who come from Singapore Management University. The title of the paper is Deep RL Approach to Solve DVRP with Stochastic Customers, and it's submitted under Novel Application Track. The motivation behind this research paper is as follows. In real-world urban logistic operation, changes to the routes and paths occur in response to dynamic events, such as there's a new request coming in, there's cancellation of requests, or even changes to the traffic condition. To ensure customers' demands are being met, logistics service providers need to dynamically respond to these changes quickly and sometimes instantaneously. So our research work is really about helping this logistics service company to make better decisions in response to these dynamic events. So the outline of the presentation is as follows. I'll give a brief introduction and overview of the paper, dive deep into the solution approach they are proposing, share a bit more about the experimental result, and we will conclude from there. So the overview of the paper, first we'll define the problem that we are addressing, which is partially DVRP with stochastic customer, and we model it with route-based MDP. And most importantly, in our paper, we propose a solution approach. We coined a term called Deep RL with simulated annealing, DRLSA, to solve this problem. And this DRLSA consists of three main components. First is the value function approximation. Next will be the routing heuristics in the form of simulated annealing. And lastly, propose a state representation based on cost of remaining routes. I will go into detail of each of these components later on in the presentation. So the problem settings that we are addressing here is actually a VRP with the following settings: partially dynamic, known, and also dynamic stochastic customers, meaning that at the start of the day, a logistic company will already have a list of known customers, and throughout the day, when the vehicles are doing the delivery, there will be new customers that are coming in dynamically. And this problem involves multiple vehicles, and there are time windows consideration for delivery and lunch hour, and it's also a same-day delivery. So the objective is to compute the updated routes or delivery plans whenever there is a dynamic events occurring to minimize the travel time, waiting time, and the penalty cost for time window violations. And we model this DVRP as an MDP because MDP mimics the real applied environment of DVRP, which is a sequential decision making. For example, a driver or a vehicle go about doing the delivery, and there's a dynamic event, which is a new customer requesting for service, then they need to make a decision sequentially as and when there's a dynamic events coming. And why route-based MDP? The difference between route-based MDP and a conventional MDP is that for the state, action space, and reward computation, you need to take into consideration the set of planned routes. This is because solution to VRP is a route plan, not merely next customer to visit. And this is important for the problem settings that we are addressing, because visibility of the entire routes is important in delivery operations, unlike ride-sharing problem. So let's move on to the proposed solution approach, which is, we call it DRLSA. DRLSA consists of two phases. First is the training phase and the execution phase of the runtime. In the training phase, or we call it value function approximation step, basically we use past historical delivery plans to approximate the value function. And having learned the value function, this will be used during the runtime, during the execution phase by simulated annealing. As you can see that simulated annealing search for a better rerouting decision that takes into consideration the immediate reward and also the future expected rewards, which is in the form of the value function that we have been approximated and learned earlier in the training phase. So the value function approximation here, we propose a non-lookup table one. We propose a neural network base with theta as the parameter vector to be learned. The reason being we propose a neural network base because the problem they are addressing is considered large and complex problem because we involve multiple vehicles and multiple constraints. Lookup table based will not be too stable because in lookup table based you need to encounter almost all possible states in order to get a corresponding value function. Next will be how do we then learn the parameter vector? We propose temporal difference learning with experience replay. And this is adapted from a vanilla version of Chuin with experience replay, which consists of two value function networks and the experience replay component. But the main difference is that here we approximate the value function instead of approximating the Q function. So the next logical question will be, why then we approximate the value function? This is because approximating Q value in our problem setting is not suitable because a decision comprises rerouting and not explicit action per se. For example, in this scenario, customer 6 requests for a service. So the action is not merely where to insert customer 6. The decision involves rerouting even the existing customers. So customer, for example, 3 and 4 may be swapped, and even 5 can be swapped. So the action involves rerouting and not an explicit action. So offline policy, off-policy temporal difference learning like DQN is not applicable directly here. Next, simulated annealing. Why simulated annealing? So we propose SA as a way to find good rerouting decision quickly and effectively. So instead of calculating the true mean by brute force enumeration of all routing sequences, we propose a routing heuristic in the form of SA. And again, to emphasize here, the value function that you have been learned earlier will help to guide SA search to find rerouting decision that takes into consideration the immediate reward and also the future expected reward. And as you can see, this framework allows other routing heuristics to be used instead of SA. Last part of DRSA will be the state representation. Again, the idea of is to explore the structure of the problem to extract distinctive feature of the state so that two different states may require two different policies. And it's important also to reduce the state space. So here, in this paper, we propose a state representation based on time, cost of remaining routes, and penalty cost of time variation for each vehicles. I think time is quite an obvious feature that is important in affecting rerouting decision. So I'll elaborate more with the other two features, cost of remaining routes and the penalty cost for time violation. First, rerouting decision is impacted only by the remaining routes of the vehicles. The earlier routes that have been served will not impact the rerouting decision whenever dynamic events occur. And the next question will be, what if two different routes having the same cost? In this scenario, for example, here scenario 1 and scenario 2 both may have the same cost of remaining routes, but the decision to insert customer 6 will depend on the immediate reward and also the value of the post-decision state, which are different in both scenarios. Next, I propose the use of total penalty cost to serve as a proxy to time window requirement. So in this case, scenario 1 and scenario 2 both might have same remaining cost of remaining routes, exactly same sequence of customers, but customer 6 and 6 prime might differ in the time windows requirement. So even if customer 6 and 6 prime are inserted in the same sequence, in the same order of the route, both scenario 1 and scenario 2 both have different states because the total penalty cost of scenario 1 and scenario 2 are different. So next will be the experimental results. First, we benchmark our proposed approach against one offline and one online approaches. The offline approach in the form of approximate value iteration, AVI, and online multiple scenario approach, MSA, and of course, myopic approach. So the design of the experiment, we try to vary the degree of dynamism, which is the proportion of the dynamic request, and the performance measure that we use is actually improvement over the myopic. So at the experimental results, first we compare against AVI. Here, when DOD's degree of dynamism is equal to 0.7, DRSA outperform AVI even with less training episode. But when the DOD goes to 0.5 or below, DRSA performs poorly. And this is consistent for the both methods. For DOD that is less 0.5 or less, and both methods does not seem to perform better than myopic. And we can infer that lower DOD means that stochastic order are less likely to occur in such a way that is very difficult, challenging to anticipate a rarely occurring event. Next, we compare DRSA against the online method MSA. Again, DRSA outperform MSA for both sample sizes 50 and 100. Of course, this may not be the apple-to-apple comparison, but nevertheless, MSA needs a larger sample size and longer competition time to outperform DRSA. So here we can conclude that actually online method like the MSA might not be suitable in problem setting because of the need for instantaneous decision making. So offline approaches that we are proposing is suitable for the problem setting. Next, we try our proposed approach against larger DODs and problem sizes. And DRLC perform consistently well with increasing dynamism and problem sizes. So how do we compare, how our results, our proposed approach compare with other works? In this paper, these authors summarize the different offline approaches in solving such a similar kind of problem. And most approaches in the literature achieve an improvement in the region of 5 to 10% for customers around in the region of 30 customers. So our experiment shows that our proposed approach is comparable with those in the literature. So to conclude, we show that we apply a deep RL approach to solve a DVRP with stochastic customers. And this is just a recap overview of our solution approach of DRLSA with the 3 main components and contributions in the paper. And we are able to show that it performs well with relatively small training data and with increasing dynamicity. So in future works, we need to evaluate this proposed approach against other data sets, larger problem, and other optimization problem. And of course, our main goal in our research is really to find whether there is such a generalized learning framework for a real-world dynamic scheduling and routing problem. That's all for my presentation. Thank you.